beginner or geek, we have to improve our problem solving skill, because for us, never stop learning is our motto. Maybe you need your math skills, code efficiency analyzing, tree algorithm. Follow me in my channel where I explain in details the logic behind the solution of some problems. Hello friends, my name is Murad Nwayli from Think and Code. In this video, I offer to you a unique and beautiful explanations of the DIV.4 886 contest from Codeforces, where you need your math skill, graph theory, recursion, code efficiency analyzing to solve some problems. Just focus and be patient and passionate. Let's get started. Problem A to my critics. This is the problem statement. We have a 3 digits A, B, and C. Since math isn't his strongest point, he asks you to determine if you can choose any 2 digits to make a sum greater or equal to 10. Output yes if a pair that make the sum is 10, no otherwise. What we see here for this example, we have 3 digits and we A, B, C, and we're trying to determine if A plus B greater or equal to 10, or A plus C greater or equal to 10, or B plus C greater or equal to 10. So in that case, we return yes, otherwise we return no. For example here, 8, 1, 2, we output yes because 8 plus 2 greater is equal to 10. For this example, for A is equal to 4, B is equal to 4, C is equal to 5. We answer no because we can't. There is no pair which is their sum is equal, greater or equal to 10. As you see here. Same for 0, 0, 0. For 9, 9, 9, we output yes because we have 9 plus 9 is greater or equal to 10, and so on. It's very simple. The pseudocode of the problem. We can use this formula. If A plus B greater or equal to 10, or A plus C greater or equal to 10, or B plus C greater or equal to 10, we output yes. We have this here at least 1, 2. At least if there is at least 1 2, we output yes. Otherwise we output no, because we use or C. Or here, or use or. This is the code in C++. There is another solution. This is the Codeforces solution. We use this formula: A plus B plus C minus the minimum between A, B, and C. If this formula give me a result that is greater or equal to 10, we output yes, otherwise probability 2. Why this works? Because the minimum of A, B, C is A. If is A, so the formula become A plus B plus C minus A greater or equal to 10, so B plus C. Or the minimum could be B. If the minimum is B, so the formula become A plus B plus C minus B greater or equal to 10. We check this. So we check, in reality, we check a plus c greater or equal to 10. Or the minimum is c, minimum of ABC is c. So the formula will be a plus b plus c minus c. So it will be a plus b. Okay, this is very clear here. This makes sense. So this is the code of this solution. Problem B, 10 words of wisdom. Problem statement, we have an participant. Each participant I, such as I is between 1 and n inclusive, give a response of I length and qi query. The participant whom response does not exceed 10 words of length and has the highest response quality. This is our task, our output. For example, here we have the first participant response with the, for example, 1 word, which with the two quality, 2 degrees of quality, if we can say that. The participant number 2, his response contains 5 words with the 3 quality. This participant number 3, 12 words with 10 quality. Participant number 4, 5 words with 8 quality. Participant number 5, 3 words with 8 quality. We're going to skip this because this is the highest quality as you see, but its response exceed 10. The response must be less or equal to 10 words. So we'll skip this. The rest, the highest quality is this one. The first one met here. This is with the participant number 4. This is the highest quality. So participant number 4 is the winner. This is the code. This is our output. This is our input. R and Q, the response and the quality. If the response is less or equal to 10 words, so we update the quality Q, the highest quality MX quality here, -1. Answer is 0. Answer, it could be the order of the participant, the number of the participant, the input. As you see here, for I from 1 to n, I read the response and the quality. Every time I found a quality Q that's greater than my maximum, I update that maximum by that quality. And of course, I update the answer with the order or the counter I of that participant of which has this quality. Problem C, word on the paper. This is the problem statement. We have 8 by 8 grid of dots. A word consisting of lowercase Latin letters is written vertically in one color, from top to bottom. What is it? So here we have a grid with consisting of dots, and in that grid we have letters written in the same color. So we have to output that word. For example, here we have here this our grid of dots. We have, as you see, these letters on the same color. The word is last, as you see. The logic is very simple here. We run over all the matrix. If we encounter a letter, then display it. Let's run this. This is a letter no. This is a letter no. We go to the next letter. The current letter is the current cell of the matrix is in red. The gray ones are visible. So we are in this position. Yeah. Yeah. This is not a letter, so we go to the next. Not a letter, not a letter. We have a letter here, so we display it. We go run over all the matrix like this. We encounter O here, we display it. Not a letter, not a letter. This is a letter, we display it. We go, pass, not a letter. This is a letter, we display it. Until the end of all the matrix. So this is very, very simple to implement. We run over the matrix in we have one loop and another nested loop. This is for the rows. And this is for the columns. IJ. Okay. So, because here we have len is equal to 8, we have 8 by 8, 64. So here we have 8. Every I here, every I we have 8 I's. Every I will be repeated 8 times in here. So times 8. So we have 64 input. We read that input. If the input is not a dot, we display it. And in the end, we return by carrier return. Problem D, balanced round. This is the problem statement. You are the author of Codeforces round and have prepared n problems. You are going to set problem I having difficulty AI. You will do the following process. Remove some, possibly 0 problem from the list. Rearrange the remaining problems in any order. So this is a keynote. You can rearrange the problems in any order. A round is balanced if and only if the absolute difference between the difficulty of any 2 consecutive problems is at most k. So which means less or equal than k. What's the minimum number of problems you have to remove so that an arrangement of problems is balanced? We can write the problem another words, another way. We have n problems. As we have seen, the problems are balanced, means that the absolute value of the difficulties between 2 consecutive problems must be at least a positive integer k. So if we have a set of problems, d1 to dn, this is the difficulties of the problems, which I is between 1 and n inclusive. If this set of problems is balanced, which means every di minus di plus 1 absolute value of this difference is less or equal to k. Okay, so we have to compute the minimum number of problems to remove to keep the problem balanced. Let's take an example here. If we take this set of problems, as we see here, 17 minus 3 is not balanced because k is equal to 3. The difference here is 14. So we choose, let's say, choose and remove 17. So we have to keep the 3 and 3 here. 3 and 1 is balanced because their difference is equal to 2, is less than k. 1 and 30, no. So we have to remove 30. 1 and 12, no. 1 and 5, no. 1 and 17, no. 1 and 12, no. As you see here, we kept only two integers, 3 and 1, or two problems, 3 and 1. Problem of difficulty 3 and problem of difficulty 1, and remove all the rest. So we have removed 6 here. If we solve this problem, so we can keep 1, as you see, and 3 and 5, because this part of the problems of the set is balanced, because 1 minus 3 is 2, 3 minus 5 is 2. So we have 1 through 5. Can we add 12? No. Can we add 12? No. 17? No. 17? No. 13? No. So the 3, we have these problems to remove. So we have 5 here. So as you see, the response is not the same. The answer is not the same. So the minimum number of problems is 5, not 6. So we have to solve the problem that you see, by difficulties, of course, in an ascending order. So we have to solve the array in an ascending order, and we're going to compute the number of problems to keep or to remove. This is easier than counting the number of problems to remove. Iterate over the array of problems difficulties, and we have two variables. Let's call it C and T. It will count the length of the current consecutive problems to keep, and to keep the variable to keep, it will count the length of the longest consecutive problems to keep. This is the current consecutive. This is here we count the final answer, and the answer, it will be n minus the number of problems to keep. Very makes sense here. If we have, for example, 8 problems, and we want to keep 3, so the number of problems to remove is 5. So we have, let's run this logic and see how it works. We have two variables, C and T, and to keep. Initialize to 1, why 1? Because we're going to start by problem 1. We have one problem. To assume that we have one problem on our set. So, and we will start by the first problem, and we're going to check the first problem by the second. 3 minus 1 is less to k. K is equal to 2 here. Yes, is less. So we add 1 to C and T. This is the length of the current set of problems which is balanced, 1 and 3. So we have to update, so to keep, because the maximum between, we have found the maximum which is 2. The maximum between 2 and 1 is 2. We go to next problem, check with the next one. 5 minus 3, yes, is less than k. So we have found 3 problems now, 1, 3, and 5. So we counter is 3, and the answer to keep, number of problems to keep is 3 for now. We go to 5. 12 minus 5 is not less than 2. So here we have found a set of problems of length 3, 1, 3, 5, and from this point we have just one, which is 12. So we counter is 1, but to keep the maximum for now, the maximum length of a problem of balanced problems is 3, 1 and 2, 5. Problem of difficulty 1, problem of difficulty 3, and problem of difficulty 5. We go to next problem. 12. We check the current problem by the next. 20 minus 12 is greater than k. So same here. We have just one problem which is balanced, which is for now, which is 20. And the results remain the same. We go to next problem. We check with the next one if it's balanced with the next one. Here is balanced. 21 minus 20 is less than k. K is equal to 2. Okay. So we have for now the current consecutive balanced problem is 2, 20 and 21. But our answer for now is 3, because this is the maximum we have found it in the first part of the set, 1, 3, and 5. We go to the next. 21 and 21 is less than k. So we update the length of the current set of problems, balanced set of problems, which is 20, 21, 21. We go to the next, 21 and 22. These two problems are balanced. So our counter is 4, because we have found for now this is a set of balanced problem of length 4, 21, 21, 21, and 22. And we have to update, so to keep, because we have found a set of problems longer than the first one found in the first part of this array. So we update to keep to 4. We go to the next. These two problems, the current problem in 7 and the next problem in 8, are not balanced. So we have just one problem of length 1, which is 30. 30 and 35, no, are not balanced. 35 and 36, they are balanced. So we have a problem, a set of balanced problem of length 2, 25 and 35. So we update the counter to 2, as you see, from 1 to 2. We go to the next problem. We have in 10, it's is balanced with the problem in 11, which is 36 and 36. So we have for now this sequence is of length 3, 35, 63, 35, 36, 36. And the maximum between of both 3 and 4 is we have 4 here, because for now the maximum one found until now is 4. 11, we have 36. We checked with 40. 40 is not balanced, so we stop here, because we can't go further, because we don't have 13, problem 13 here, if we go to 12. So our answer is 4, which the problem are 20, 21, 21, 22. We have to keep these problems. So all the other problems, we have to remove them. Okay. So our answer is n minus 2 keep, which is 13 minus 4 is equal to 9. This is the code. This is we put all the problems in an array A, called here. We sort this array. This is for the length of the current sequence. This is the length of the maximum sequence found the current point, and we loop all over the difficulties. And because they are sorted, we don't need the absolute value here. We're going to check if a at I plus 1 minus A at I, the value of I is less or equal than K, so we increment C and T. Otherwise, we reset C and T to 1, and we have to every time we need to update to keep with the maximum between to keep itself and the current length found at a point. And this is our answer. Problem E, cardboard for pictures. Problem statement: Marcia has n pictures. The ith picture is a square with a side length of SI centimeters. He mounted each picture on a square piece of cardboard so that each picture has a border of W centimeter of cardboard on all sides. In total, he used C square centimeters of cardboard. Given the picture sizes and the value C, can we find the value of W? Let's take here, for example, if we have 3 pictures, Marcia will mount each picture on a square piece of cardboard so that each picture has a border of W, like this. The cardboard are in green. You are given the total area C of cardboard used and the size of each picture. Find W. You have to know that the piece of cardboard goes behind each picture, not just the border, which means the cardboard in green here go totally behind the picture, not just the border of the picture. Let's see the logic of this solution. Let's say we have n pictures from P1 to Pn, and we have, of course, n cardboards. Let's say that the size, because we have square cardboards here, the size of first cardboard is x1, second x2, and until xn for the nth cardboard. So we can write we have all the area of used cardboard. So we can say that x1 square plus x2 square plus xn square is equal to C. Because if you have a square, the area of each square is here for the first one is x1 times x1, which means x1 square. So, but here, as you see, this x1 we can write it by the size. Let's call it here A1 of this picture plus this W and this W. Same here for picture number 2. A2 plus W for x2 until x, the cardboard n, an plus W. Okay, so we can write A1 plus 2W square plus A2 plus 2W square plus an plus 2W square is equal to C. As you see here, we have a remarkable product. We can develop it. And if we develop each one, we can have this formula. 4n times W square plus 4W times A1 plus A2 plus an here plus A1 square plus A2 square plus an square is equal to C. So we can have this formula for n times W square plus 4 times A1 plus A2 plus IN W for W plus A1 plus A2 square plus A1 square plus A2 square plus AN minus C is equal to 0. As you see, we have a second degree polynomial. We can resolve it using the well-known formulas. Let's take this example. We have this formula and we will apply it in this example, the example of the problem statement. We have 350. This is the C, 50 equal to C here. And we have this, the size of each picture, the 3 pictures. First picture is equal to size 3, second picture is of size 2, and the third picture is size 1. Here we can say that we can have 4n. We have 4 times 3, which is 12, times W squared, plus 4 times A1 plus A2 plus AN. We have n pictures here. We have 3 pictures here. A1, 3 plus 2 plus 1 are equal to 6. 6 times 4, 24. W minus 9, which is 3 square plus 2 square plus 1 is equal to 9 plus 4, 13. This is, I think, here 9, 13, 14. Okay. 14 minus 50, C, is equal to 36. Minus 36 is equal to 0. So we can resolve this. We compute delta, which is b squared minus 4ac, the square root of delta, and we can compute this first. We have 2 solutions here because we have delta is positive. W1 is equal to minus b minus square root of delta over 2 times a, which is equal to minus 3. This is wrong answer because W cannot be negative. So the others, we take the other solution, minus 24 minus b plus square root of delta, which is 48 over 2 times 12, which is 1. This is the answer of the problem state. W is equal to 1. Okay. This is the solution. We have 3 coefficients here. The coefficient, let's say C1 W squared plus C2 W plus C3 is equal to 0. So C1, as we have seen, is 4n, and C2 is the sum. Is the sum of all the sizes of all pictures, and the end we have times 4 times all the size, and C3, which is the square of all the sizes minus their sum minus C. So here we sum all the square of each size, and at the end of for this for loop, we subtract C from C3, and we solve this polynomial, second degree polynomial, which is we compute delta and we compute our answer. The time complexity of this is log of delta if we ignore time for taking input, because as we know, the square root is in log n. Square root of n is in log n, and if n is small, if delta is small, we can say that is in constant time. Same for if we take the input n log delta, if we consider time for taking input, or linear time if we consider this is in constant time. The Codeforces logic by a flame storm. He used another approach by using I think a binary search. He used the same formula, but using this formula he did a binary search. This is it. It's the solution. Same here, the solution in analog 10 power 9, or if we consider this concept, we can consider it as linear. This is the solution. I think it's the same solution, not very hard to understand. Problem F. We were both children. The problem statement says that Mihai and Slavich were looking at a group of n frogs numbered from 1 to n, all initially located at point 0. Frog I has a hop length of ai. Each second, frog I hops ai units forward. Before any frogs start hopping, Slavich and Mihai can place exactly one trap in a coordinate in order to catch all frogs that will ever pass through the corresponding coordinate. However, the children can't go far away from their homes, so they can only place a trap in the first n points. The points is between the points, or just one point between the position 1 and the position n. And the children can place a trap in a point 0 since they are scared of frogs. Can you help Slavich and Mihai find out what's the maximum number of frogs that can catch using a trap? We have n frogs. Let's simulate this problem and understand this problem. Each frog can hop some units forwards. For example, here frog 1 can hop 3 units forward. Frog 2 can hop just 1 unit. Frog number 3 3 units forward. Frog number 4 can hop 4 units forward, and frog number 5 can hop 9 units forward, and the last frog can hops 10 units forward. This is the position 0. Mihai and Slavich, they can't place a trap in that position. That only can place a trap between position 1 and n. We have here 6 frogs, so they can place a frog at position 1 or at position 2 or at position 3 or 4 or 5 or 6. They can't only place just one trap at one position. Okay. Let's say each position a potential trap. Okay. So at position 1, at first, at the beginning, of course, there is no frogs, and same for all the other positions. Here, I mean by this computation here. Here, the number of frogs that could be catched by Mihai and Slavich if they place a frog at that position. For example, here at position 3, the number of frogs that Mihai and Slavich can catch if they place a trap at position 3. At the beginning, there is no frogs. Okay. Frog number 1 hop 3 units forward. So at position 3 we have we can catch that frog. For frog number 1, just 1 unit. Frog number 2, sorry, just 1 unit forward. So at position 1 we can catch that frog. Could be catch if we put the trap at position 1. Same for frog number 3. It hop 3 units forward. So at position number 3 now we have 2 frogs. The frog number 4, frog number 5 and 6 that can't be catched because they can hop. The number of units is greater than 6, which is the number which is n. Because as we have said, nimaje and leverage they can only place a trap between 1 and n, 1 and 6 for this example. So these two can't be catched. So for just for one round here, if you can say this, one round, if they place a frog, if they place a trap at position 1, they can catch this frog. At position 2, they can't catch. There is no frog to catch here. At position number 3, they can catch 2 frogs if they place the trap at position 3. And if the trap is at position 4, they can catch only this frog. Let's continue. Frog number 1 will hop another 3 units, so it will be at position 6. Frog number 2, 1 unit, so it will be at position 2. Frog number 3, 3 units, so it will be at position 6. Frog number 4, 4 units, so it will be at position 8, so they can't place a trap at that position, so the frog it can't be catched. So for this round, as you see, we have, if they place after round 1 and round 2, if they place a trap at position 1, they can catch only 1 frog. If they place a trap at position 2, they can catch 1 frog. If they place a trap at position 3, they can catch 2 frogs. At position 4, just 1 frog. At position 5, no frog to catch here. And at position 6, 2 frogs. Let's continue. Frog number 1 will hop another 3 units, so it will be out of range. Frog number 2, it will be at position 3 because it can hop only just 1 unit. And frog number 3, another it hops 3 units forward, so it will be out of range. So for this round, after 3 rounds here, if the trap is at position 1, just 1 trap. Position 2, just 1 frog. Sorry. If the trap at position 1, we can catch just 1 frog. If the trap at position 3, we can catch 3 frogs. At position 4, 1 frog. Position 5, 0. Position 6, 2. So the answer here, because this frog catched, we can say, if we continue, there's no vein to continue here. If we continue, it will be here 2, 1, 3. Okay, but here, as you see, we have finished with this answers. So we can say that the maximum frogs that nimaje and leverage can catch, it's a 3. If they place, for example, a trap at position 3 or at position 6. Okay. So we have to code. The code must give me this answer. These answers, and I will find the maximum between these values. The data structure that we can use here, it's very clear that we will use an array to compute this. An array from 1 to 6. For 0, we have 0. We const. And the logic of this now, we will declare an array of answers of length 6, we can say here, but as you know, most programming language starts by 0, the index, so it will be 0 here. This case, this cell will not be used because we will only use from 1 to 6. This is because Slavic and Mihai, they can place a trap only in these one of these positions from 1 to 6. So if we have frog number 1 have 3 hops forward, so it will be at position 3 or at position 6. Frog number 2 can hop only 1 unit, so it could be at position 1 or at position 2 or at position 3, but we have the previous frog, so it will be 2 here, or at position 4 for frog number 2, or at position 5, sorry, or at position 6. We go to the next frog. It could be it hops 3 units forward, so it could be at position 3 or 6. For this frog, it hops 4 units forward, so it could be at position 4. For these 2 frogs, last 2 frogs, this one hops 9 units forward, so it's out of range. You can't place a trap at position 9. Same for this frog. Okay, so then we will compute the maximum between these values in the array answers, which is 3. This is the pseudocode. We have here the array that contains the hops of each frog. So for the ith frog, we have the AI hops in the array A. Okay. We have our array of answers of size n+1. This will contain the maximum number of frogs could be catch. Then we run over this array, as we have seen in the previous presentation, previous slide. We run over the array of hops. If the hop at that position is greater than n, so we do nothing, just continue to the next frog, to the next hops of that frog. And for each position from AI to n, but here we have to step by AI. Why? To have the exact or the right hop. For example, if the frog number 1 hops 3 units forward, so we have the area from 1 to 6, for example. If the hops the frog I hop 3 units forward, so this we will add 1 at 3 and add 1 to 6. Okay, so we go from 3 position 3, and we go by 3. This is the hops here, the hop of that frog. Okay, and every time we update the answers of that element x, we compute the maximum, which is the number of frog, the maximum number of frog that could be catched by Mihai and Slavic. And finally we return that maximum. If we analyze this pseudocode, we have, as you see, we have two loops. This loop and this inner loop. So for I equal to 0, the inner loop runs this one, this inner loop. The inner loop runs n minus a0 over a0 plus 1, because as you see here, the number of iterations or this loop depends of the element ai, and we know that ai is an integer between 1 and n. Okay, if we make a process of the AI, we can delete this, and in the beginning we put in the array A only the number of hops less than n, between 1 and n. Okay, so if I is equal to 0, the inner loop runs n minus a0 over a0 plus 1. Because why this n minus a0 over a0 plus 1? Because we have ai is in this range. If ai is not in this range, the number of iterations will be n over a0. Okay. For I equal to 1, the inner loop runs n minus a1 over a1 plus 1, and for the last one, I equal n minus 1, inner loops run n minus an, the element at the position n minus 1 over the same element plus 1. So the whole time, the overall time number of iteration or time complexity, we can say that the formula, it will be the sum of this all values. Let's say that this sum gives me this formula where C and D are constant. Okay. So in the best case, C is different than n if C is not equal to n. So we have n plus a constant n, a constant C times n minus constant D over constant D. So the time in the best case will be omega of n in linear time. The worst case, if nc is equal to n, so it would be here n times n will be n squared. So the worst case, the time complexity is big O n squared, which is quadratic. Here I want to thank this guy Nimaje from LiberaChat, the IRC server LiberaChat, from Channel Algorithms, who discussed with me this the time complexity of this pseudocode. Okay. If you call this, we will have a time limit exceed. So we have to speed up this this implementation. How to do this? If we come back to this example, as you see, number 3 is, we have 2 times number 3. The idea here, instead of computing every time number 3 when we found it, we add 1. Just in the first time, we will compute the number of appearance of each element in the array A, which is the number of hubs. Okay, for example, for this example, we have this input 3. We have appears 2 times, 1 time, 4 1 time. Okay, and we run over that map. When we found the 3, we go directly to 3 and we add 2. We have found 1, we go directly to 1 and 2 and 3 and 4 and 5 and we add 1. We have 4, 1. We go directly on 4 and we add 1. The idea here is to, instead, if we have, for example, if you have, for example, 3, 1, 3, 3, 3, 3, 3. Okay? So instead, go on element by element. We compute the number of 3's. Here we have 6 and just 1, 1 for this example. Okay? So we go directly to 3. We add 6 here. 6, 6. And we go to we go by 1 here, we add 1 here, it would be 1, 1, 7, 1, 1, 7, and that's it. We have 2 iterations instead of 7 iterations. Okay. Same, the maximum is 3 here. So the pseudocode, first we have the hash map counts. We're going to count the number of appearance of each element. If a is less than n, so we count it. Element, how many elements we have, how many AI. This is for the n, for the maximum. And now for we iterate over that map. For each pair, as you see, a map, it contains a pair of key and value. Here it depends, it's C++ like here, but it depends on your language that you implement your solution. So same here for the last one. For every x from P0, which is the number of hubs, Pi to n step P0, so we have by the number of hubs here, P0. The key, because the key is the AI, which is the number of hubs of each block. The answer of x will be answer of x plus the value of that, how many, the number, this is the number of appearance of each hub. Okay? And we update the max. So in the worst case, all i's are equal to 1. And the last one, for this code, the worst case, if we have a the number, the array a are all ones. Okay, so this in this case would be n squared. So, but in this case, in this implementation, it will change to be linear because we have compute the number of 1. We have, for example, z1s. Okay, so we add z to 1. Okay, just we have here we have one iteration because we have one element in that map, and we go from 1 to n step by 1. So we have here an iteration. So we have linearity. There are the cases where i's are different. We have OM, where m is the size of the map count. Here we are sure that the size m is between 1 and n. It couldn't be greater than n. It's very clear. It makes sense. Okay, so the whole time complexity, it would be m, which the size. It would be m, the size of this map, times n, which is the number of iterations, the maximum number of iterations that we could have here in this loop. So m times n. So in the best case, m is equal to n. The worst case, m is equal to. Okay. This is the code. As you see, this code is accessed. Problem J, the moon and star. Let's see the problem statement. A compass points directly toward the moon and star. It can only point in one of 8 directions. The 4 cardinal direction, north, south, east, west, or some combinations, northwest, northeast, southwest, southeast, otherwise it will break. There are n distinct points with integer coordinates on a plane. How many ways can you put a compass at one point and the moon and star at another so that the compass does not break? Let's see an example here. Let's understand that the problem. If we have this input, we have some points here. We want to know how many directions we can make with using these all points. 0, 0, 0, 2, 2, minus 1, 5, minus 1, 10, 2, 11. Let's make, I'm going to use a brute force approach, which means I'm going to test each point with all other points. Let's start by the point 0, 0. It's our compass. And from 0, 0 to 2, 2. As you see, we can make a direction here to the northwest, northeast. So we have northeast, so we have one direction. 0, 0 and minus 1, 5. There is no direction, as you see in this presentation, in the picture. 0, 0, minus 1, 10. There is no direction. 0, 0, 2, 11. Also no, there is no direction. We go to the point 2, 2. Now from 2, 2, we're going to check 2, 2 with all the other points. 2, 2, 0, 0. We can make a direction which is southwest. So we have another direction. I have 2 directions now. 2, 2, minus 1, 5. We can make a direction to the northwest. We have the 3rd direction. 2, 2, minus 1, 10. No direction. 2, 2, 2, 11. We have, as you see, we have a direction to the north. So this is the 4th direction. We go to the minus 1, 5. Minus 1, 5. With 2, 2, we can make a direction to the southeast. Minus 1, 5. So we have 5 direction. Minus 1, 5 with 0, 0, there is no direction. Minus 1, 5 with minus 1, 10, we have a direction to the north. So we have 6 directions until now. And minus 1, 5, 2, 11, no, there is no direction. Let me see. Minus 1, 10 with 0, 0, no direction. With minus 1, 5, we have a direction to the south. We have this direction number 7. Minus 1, 10 with 2, 2, no direction. And minus 1, 10 with 2, 11, no direction. We go to the point 2, 11. 2, 11 with 0, 0, no direction. 2, 11 with 2, 2, there is a direction to the south. This is the direction number 8. 2, 11, minus 1, 5, no direction. 2, 11, minus 1, 10, no direction. So with all these points, we can make 8 directions. Okay. Observation number 1, we have this observation. If I have 2 points with the coordinates x, y, y, I, and point B with coordinate x, b, y, b, if AB is a valid direction, so BA does 2, which means BA is a valid direction too, as we have seen. If, for example, I have from 0, 0 a valid direction which is to the north east, so I have another direction to the north southwest. So if I found a direction, so it makes sense that I have another. From this, if I have direction between 2 points from this one, this direction, so right direction is in this way. Okay, this is the first observation. The other observation is about the lines of each direction. It's an affine function. We know the affine function. We can write it like this: y is equal to a times x plus b. Y and x are the coordinate of the points. A and b are constant. If I have 2 points, if I know the two coordinates of the 2 points A and B, so I can compute the slope. This is called the slope of this line, and this is a constant. So the slope, I can compute the slope using this formula: yb minus ya over xb minus xa, if of course ab minus xa different of 0, otherwise equal to 0. So now, if for example I have the direction west east, this one, the west and east direction, west east, this line. Okay, so this is horizontal line. It could be here or here or here or any other line. Essentially, we have a horizontal line, which means y is equal to b, which means the slope a is equal to 0. As you see here, there is no slope for this line. So the slope a is equal to 0 because y is constant here. You see, y is always constant. X is x changes, but y is constant. So y is equal to b. The slope is 0. Same for the line, vertical lines, north and south. Direction north to the north, or direction to the south. Same, there is no slope here. A is equal to 0. X is constant. We have the same x for all the line here, on the point of this line. Same here. We have the same x. For every vertical line, we have the same x. So we can say that x is equal to b, there is no slope. Same, slope is equal to 0 here. For southwest, north, east, this line, or this line, I can say, for example, this one or this one. There's a slope for this line, as you see. The slope of this line is equal to 1. Because here, as you see, y is equal to x for this line. And for this line, y is equal to x plus b. Of course, b changed for this line. But let's call it line 1 here. So here b1. If this is line 2, this is y is equal to x plus b2. Because that is not the same b, but the same slope. As you see, every line has the same slope. Assume, guys, that you know, of course, what's the meaning, the real meaning of the slope of the line. The other direction, the southeast, northwest. This line, or for example, this line or this line, same line here, so here or this line. As you see, there's the same slope here for these lines. Okay, the slope is equal to -1 here. For this one, same here, equal y is equal to minus x. A is equal to -1 plus b1. If I call it 1, line 2 minus x plus b2. Okay, b will be different for every line, of course, because they're not the same position, but they have the same slope. Okay. So from this, we can use this logic. For every point, as I did in the first presentation, we're going to brute force the same from each point. I'm going to test if I can have the 4 vertical or horizontal or diagonal slope 1 or the other diagonal slope -1. So let's start from this point. I want to check it with the 0022. 0022. If I compute the slope using this formula, I found the slope is equal to 2 minus 0. So the slope is 0 here because 0 minus 0 is equal to 0. I can't divide by 0. So the slope is 0. So I have a direction here. I don't care what's the direction, but I have a direction. And this example, the slope is equal to, let's check together, the slope is equal to what? 2 yb minus ya over 2 minus, this is not 0, the slope is equal to 1. Sorry for this, guys. Slope is equal to 1, which means that this line, there is no b here. So I have a direction. Why I put 2 here? Because I will compute directly the other direction. As I said, observation number 2. We can come back to the observation number 2 here. Sorry, this one. This observation number 1. If I have a direction AB, so I have a direction BA, the same direction, the opposite direction, the same. So I have a direction from 0, 0 to 2, 2, which means I have a direction from 2, 2 to 0, 0. So we can compute directly. We go to 0, 0 minus 1, 5. The slope is equal to minus 5. There is no direction here. 0, 0 minus 1, 10. Slope is equal to minus 10. No direction. 0, 0, 2, 11. Slope is equal to 5.5. No direction. We go to 2, 2. 2, 2. I will test 2, 2 with minus 1, 5. Of course, I will not test 2, 2 with 0, 0 because I did it in the first line, the first check. 2, 2, 2, 2 is the same point. So I go to 2, 2 minus 1, 5. 2, 2 minus 1, 5. The slope is equal to minus 1. So I have a direction. So I add 2. 2, 2 will be 4. We have 2, 2 from 2, 2 to minus 1, 5. And from minus 1, 5 to 2, 2. 2, 2 minus 1, 10. The slope is equal to 2.6. There is no direction. 2, 2 to 11. Slope is equal to 0 because I have here 2 and 2 on the x's. I cannot divide. So slope is equal to 0. So I have a direction here, a vertical direction from the south to the north and from the north to the south. We have 2 directions. That's why I can from 4 I add 2, becomes 6. So I will check. So the point minus 5, minus 1, 5 with minus 1, 10. Slope is equal to 0. Same here. Here I have a vertical direction, north, south, south, north. So it will be 8. The number of directions are now. Minus 1, 5 to the point 2, 11. Slope is equal to 2. There is no direction. And minus 1, 10 and 2, 11. Slope is equal to 0.3. There's no direction. And this is the end of this example. As you, for this input, I have 8 directions as we have found in the first presentation, first slide. This is the pseudocode of this code. I will run from 0 to n minus 2. Why n minus 2? Because I add to I plus 1 here. And from j to I plus 1 to n minus 1, I will compute the the first point, let's call it this point A, this is point B, the coordinate is point A, the coordinate is point B. So point A, coordinate XA is at the array point A, point I0, is I, and YA is point I1. And for point B, it will be the counter, this, we are going to use this counter J. J0 point J1. I will assume that the slope is equal to 0, and if I found that xb minus xi different to 0, I will change the slope. If the slope is equal to 0, or slope is equal to minus 1, or the slope is equal to 1, I will add to the counter. Counter is equal to 0 at the beginning. Initialize the counter here. Counter is equal to sound to 0. Okay. Type complexity of this code is quadratic, and the space complexity I have to use the points, the array of pair, the inputs. I will put the arrays in this array, and in this array I will put the points in pair here. X1, x0, y0. This is the first pair until xi. Way up. Okay. If I use this code, this logic, you will get a time limit exceeded because we have space complexity big O and square in the worst case. Let's see how to optimize this logic. The first observation. Let's say that we have 2 points in the same line, vertical, horizontal, or diagonal. The diagonal of the slope 1, or the other line with the slope minus 1. How many directions we can make here? We can make 2 directions. South, for example, if this is the southeast, this is northwest. We can make to the southeast, to the south, southeast to the northwest. This is the first direction. The other direction from the northwest to the southeast, as you see here. So, in total, for this 2 points, I have 2 directions. What if I have 3 points? We can make southeast, northwest, northwest, southeast times 3, which means this is southeast to northwest. 1, 2, 3, 4, 5, 6. So I have 6 directions for this points, for this configuration. 3 points in the same line. If I have four points, I have this direction: 1, 2, 3, 4, 5, 6. 6 here, same here, 6. So we have 12. Okay. If we come back to the first number, we can write 2 is equal to 2 times 1. 6. Which is 2, it is the number of points in the lines. On the line. 2 times 1. We have 3 here, 3 points, so we can write 6. 3 times 2. We have 4 points in the same line here, so we can write 4 times 3. If we continue with 5, we will find 5 times 4, 5 times 4, 20 directions. So we can say for m points in the same line, we can make m times m minus 1 directions. Of course, we have to prove this. We prove it quickly. Let's assume if Pm is the 4 m points in the same line, we can make m times m per direction. Prove Pm is 2. We're going to use the proof by induction. It'll be easy to prove it. we can conclude, we can observe that PM is a Pronic integer. What's mean the Pronic integer? This one. A Pronic number is a number that's the that is the product of the two consecutive integers. Is a number that is the product of two consecutive integers. That number is the form n times n plus 1. This type is, for example, here, as you see, 2 is a Pronic number because 2 is equal to 2 times 1. 6 is a Pronic number because 6 is equal to 3 times 2. Take another. This 30. 30 is a Pronic number because the product of 6 times 5 or 5 times 6. So in general, we can say the Pronic number n, if a number is Pronic, n is equal to x times x plus 1. Is the product of two consecutive integers. So we have n and n2 are two consecutive Pronic integers. If we have n and n1 and n2 are two consecutive Pronic integers, but n1 and n2 are integers, of course, and n1 is greater than n2 is greater than n1. So we have n1 could be written by this formula, x1 times x1 plus 1, because n1 is a Pronic, and n2 is directly consecutive to n1. We can write it by x2 times x2 plus 1. Because n1 and n2 are two consecutive Pronic integers, x2 is equal to x1 plus 1. So if we subtract n2 minus 1, we can find is equal to 2x2. Let's come back here and take two Pronic integers. For example, two consecutive Pronic integers. For example, these two numbers. 56 and 72. 56 is equal to I think 7 times 8. I forget this. Yeah, 7 times 8. Yes. Then 72 is equal to 8 times 9. Yes. And this one is 8 times 9. Okay. These two integers are Pronic. Two consecutive Pronic integers. We can write this is x1, this x1 plus 1, and this is x2, and this is x2 plus 1. If the two integers n1 and 2 are consecutive, so we can say that x2, this one, is equal to x1 plus 1, or this one. As you see, they are equal because there are consecutive Pronic integers. As you see, 1 plus 2, 2 plus 3. This is the Pronic integer, the list of Pronic integers we can make by 1 times 2. The next one 2 times 3, which is 6. The next one 3 times 4, which is 12. The next one 4 times 5, which is 20. As you see, if these two Pronic integers are consecutive, we can say that x2 is equal to x1 plus 1. So we can prove now by induction. The base case where we have two points in the same line, we have two directions. This is true. Induction step, we're going to assume that the sentence is true. So we have to prove that Pm plus 1 is true. And we have seen that Pm is a Pronic integer. So Pm and Pm plus 1 are two consecutive Pronic integers. Okay? So we can say that Pm plus 1 minus Pm is equal to m times m1 minus m minus 1 times m. Okay? Which equal to 2m. We have the same formula here as you see here. So we have proved by using these definitions of Pronic integers and the definition of the sentence, which is using this formula, we have proved that these two integers, they are Pronic. We have proved this using the definition of Pronic integers, and we have proved that the difference between two consecutive results is equal to 2m, which is the definition of Pronic integers. So we can say that this formula is correct. Okay. The observation number 2 of the optimization. If we have y is equal to x plus b, the slope times x plus b, b is constant. If I have a direction to the north, east, or east, north. Sorry, here not northeast. I'm saying by north south here. Right on this south. A direction from the north to the south, south to the north, we have the same axis, which means points are on the same line, which means the slope is equal to 0, x is equal to b. Same for the east-west, or west-east. All the points are the same y's, so the points are on the same horizontal line. So we can say that y is equal to b. Okay. For the other directions, southwest, southwest or northeast, this direction here or here, the slope is equal to 1. So we can say that y is equal to x plus b. So we can say that y minus x is equal to b, constant b. The other direction, southeast, northwest, points are on the same line with the slope minus 1. Y is equal to minus x plus b. So y plus x is equal to b. Okay. What we're going to do now, we're going to use a map to count the number of points with x and y, and y minus x and y plus x, which means we're going to count the number of points in the same vertical line, the number of points in the same horizontal line, the number of points in the same line with slope 1 using this formula, and the same number of points on the same line with slope minus 1 using this formula, y plus x. So we're going to use a map horizontal for points in the same horizontal line using y here, horizontal line, because y is equal to b, y is equal to constant. So using the coordinate y for each input. For the horizontal line, we're going to use x. I think I have this mistake here. No, vertical lines. For the point on the same vertical line, we're going to use x, because x is equal to b, constant. So we're going to compute that x, how many x we have, and how many points we have in the vertical line, using that formula. How many points we have in the same horizontal line, and how many points we have on the same line with slope 1. So we're going to use this formula, y minus x, as we have seen here. Slope 1 is equal to this formula, so y minus x is equal to constant b. And y plus x, how many points we have in the same line with slope minus 1. So if I have a point that have the same y coordinate, which means they are on the same horizontal line. If you have some points in this, they have all the same x, which means they are on the same vertical line. If I have a point with the formula y minus x give me the same constant b, which means these points are on the same line with slope 1. And if I have a point with the formula y plus x give me the same result of the same constant b, which means these points are on the same line with slope minus 1. This is the code that you see here. For every input we're going to compute this points on the lines, and at the end we're going to count using the number of the points in that each map. We're going to count with this formula p point second times p point second minus 1, because as we have said in the observation, I think here, not here, here. For a line contains m points, we can make m times m minus 1 direction. And here, these maps help me to count the number of points on each line: vertical, horizontal, diagonal with slope 1, diagonal with slope minus 1. And after that, we compute how many direction we can make using each number of points in the same line. Problem H, the third letter. This is a cool problem. Let's see it together. In order to win his toughest battle, Monsieur came up with a great strategy for his army. He has n soldiers and decided to arrange them in a certain way in camps. Each soldier has to belong to exactly one camp, and there is one camp at each integer point on the x-axis and on the x-axis. The strategy consists of m conditions. Condition I tells that soldier AI should belong to a camp that is situated the I meters in front of the camp of that person BI belongs to. If the I is negative, then AI's camp should be at minus the I meters behind BI's camp. Now Mercier wonders if there exists a partition of soldiers that respects the condition, and he asks for help. Answer yes. If there is a partition of the n soldiers, then satisfies all the n conditions and no otherwise. Okay, let's understand the problem. We have here 5 soldiers from 1 to 5, and we have 3 conditions. All these 3 conditions here: I, soldier I's, B's, and distance. Okay, the first one here tells us that soldier 1 is in front soldier 2 by 2 meters. We can put, for example, soldier 1, if we put soldier 1 at minus 1, so soldier 2 should be at 2 units behind soldier 1, or soldier 1 should be 2 units in front of soldier 2, because here we have 2. This can be, this distance here is this one. Okay, 2, 3, 4 indicates that soldier 2 is in front soldier 3 by 4 units. So here we have to count from soldier 2, 1, 2, 3, 4. 1, 2, 3, 1, 2, 3, 4 here. Unit 1, unit 2, unit 3, unit 4. So soldier 3 should be in that place, in that position. Okay. 4, 2 minus 6 tells us that soldier 4 must be behind soldier 2 by 6 units. So behind from in this partition, but by 6 units. 1, 2, 3, 4, 5, 6. So soldier 4 must be there. Okay. As you see here, soldier 5 is not mentioned, so we can place it anywhere, in any position in the x-axis. Okay, you can put it here, for example, with soldier 2 or any other position. In this case, we answer yes, because there is an arrangement of the 5 soldiers that satisfies all the 3 conditions. Let's see another example. For example, this one. Here, 1, 2, 2 means soldier 1 is from soldier 2 by 2 units. 2, 3, 4 means that soldier 2 is in front soldier 3 by 4 units. So soldier 3 must be at the position 5, because soldier 2 is at the position 1. So here we have 4 units. 1, 2, 3, 4. This condition is same here if soldier 4 is behind soldier 2 by 6 units. 1, 2, 3, 4, 5, 6, as you see. Here in this condition, 5, 4, 4 means that soldier 5 is in front soldier 4 by 4 units. You see here 5 and 4. The distance is 4. Soldier 5 is in front soldier 4 by 4 units. The problem is here. Can we make this condition? This condition tells us that soldier 3 must be at the in front soldier 5 by 10 units. But here, just by doing these conditions, we have this arrangement. So we cannot do this, because soldier 3, 5, and 3, the distance between them is 2, not 10. So soldier 3 must be using these conditions. Conditions here. Soldier 3, after applying these conditions, soldier 5 must be in front soldier 3 by 2 units. But here we want 10, so we cannot execute or satisfy this condition. 3, 5, 10. So the answer here is no. The condition 3, 4, 10 violates the previous arrangements. Okay. I hope the problem is understood. Before I show you the solution, I'd like to make some observations. If we can make an arrangement using these conditions, it means that the distance between 2 nodes remain the same regardless of the taken path. For example, here, as you see here in this image, in this arrangement, the distance between 1 and 2, soldier 1 and soldier 2 is always 2. Okay, so as here, from 1 to 2 is equal to 2. Okay, let's take another path. From 1, passing through 2, passing through 3, and back to 2. here from 1, 2, 3, 2. We can say this is the distance between the path between 1 and 2. We must find 2 the distance. Let's check. 2 plus 4 minus 4 is 2, which is here. This is 2. Let's take another path from 1, 2, 3, 5, 4, node 6, and back to 2. So here from 1 to 2, passing through 3, 4, 5, 4, 3, 5, 4, 6. We compute it. If we can find is the distance is here is 4, 8. 8 minus 3 is 5. 5 minus 3 is 2. So the distance is 2, using also this path from 1 to 2. Okay, as you see, regardless the path that we take, the distance between two soldiers or two nodes must remain the same. Of course, on condition and that all these conditions we can make an arrangement with these conditions. Let's take the other case where we can't make an arrangement because of this edge here, or this condition here, because the distance between 3 and 5 is 2, is not 10. Okay, so this is the mistake here. Let's say to go. So the distance between 1 and 2, let's take 1 and 2, is 2. This is correct until now. Okay, let's take another path. So the distance between 1 and 2, we go by 3, 5, 4, and 6. Let's check the distance here. Say here we have 6. 6 minus 10 is minus 4. Minus 4 plus 4 is 0. 0 plus minus 6 is minus 6. We have found minus 6 here. Or the distance must be 2. So this is incorrect. You can say when we found the thing like this, when we find a different distance from the real distance, not the same. So we can say that we cannot make an arrangement here. It's false if you say that. Okay. How we can do this? Let's go to the first. Let's back to the first case here. So we're going to create an array of distances. Okay, which distance at I is contained the distance between soldier 1 and soldier I. We have here the nodes from node 1, node 2, node 3, node 4, and node 5. And here let's say that we have our array lists. Okay. So the distance, the starting point here is 1. Of this graph, the starting point, we start from 1. So the distance from 1 to 1 is 0, of course. Then we go to 2. So we have to compute this distance. We have the distance at 1 because we come to 2 from 1. So we can say that 1 is the parent of 2. So we take the distance of the parent, which is 0, and we add the distance of the weight of the edge here, which is 2. So it will be 0 plus 2, it will be 2. From 2 we go to 3, same thing here, same way. We're going to compute the distance at 3, from 1 to 3, which is the distance of the parent of 3, which is 2. The parent is node 2. The distance of the parent of 3 is the node 2, and the distance from 1 to 2, at 2 is 2. So we we make 2 plus 4 is equal to 6. Same, we go to 5, can go to 5. Okay, same here. This is at 5, and this is of 3 plus the weight minus 2 here, which is 6 minus 2 is 4. So because here this is from 1 to 5 is 4. We go to 4, node 4, using this edge. This one. Okay. So here the distance is 5. It's at 5, which is 4, plus the weight here. 4 is equal to 8. We have node 6. So we go to 6. The distance from 1 to 6 is equal to the distance at 4, which is 5, plus the weight, which is 4, sorry. This at 4, which is 8, sorry, plus the edge minus 3, which is equal to 5 here. Okay. And we go back, we can go back to 2. Here, 2 is visited, as you see. Okay. What we can say here? We want to check if the distance from 1 to 2, we're going to compare the distance from 1 to 2 and the distance from 1 to 2 passing by 3, 4, 5, and 6. Plus the weight from 6 to 2, which is minus 3. So this is at 2 is 2. This is at 6 is 5. 5 minus 3 is 2. They are equal, so there's no problem, as we have said. The distance, if we can make, repeat, guys, if we can make an arrangement using these conditions, so the distance between any two nodes in the graph, it will be the same, regardless the path that you use. Okay, that you use. So as here, the distance from 1 to 2 is equal to the distance from here. This is from node 1 to node 2 directly, is equal to the distance from node 1 to 2, but we pass by 2, 3, 5, and 6. Okay, this is the node because this is the parent of 2. So this is 6. This is the parent of this node 2. So we will use this node plus its weight, which is minus 3. We check if because this is at 6, this is from 1 to 6. Okay, which is 5 from 1 to 6. We add the edge from 6 to 2, which is minus 3. So 5 minus 3 is 2. So 2 is equal to 2. So there's no problem. This is the idea, the general idea of the solution. Now, let's take before seeing the solution or before discussing the solution, let's say another example here. When we can't make an arrangement like this. So we can't make an arrangement. Okay. So we will see that this rule or this observation will be broken because we cannot make an arrangement using this condition. Let's see together how it happens. from 1 to 2 is 2. Let's just the array here. We have node 1, node 2, node 3, node 4, node 5, node 6. See, from 1 to 1, the distance is 0. Okay. From 1 to 2, the distance is 2. From 1 to 3, the distance, as we have said, so we compute the distance from node 2, which is 2, and we add the weight from 2 to 3, which is 4, so it's 6. Let's take the same path from 3 to 5. From 3 to 5 is minus 10, so which is 6 minus 10 is equal to minus 4. So this is from 1 to 5 is minus 4 using this condition in blue here. This edge. Okay. And we continue from 5 we go to 4. From 5 we go to 4. The distance at 4 will be 0, which is here we have minus 4 at 5, plus the weight 4 will be 0 here. And from 4 to 6, we add minus 3. So we have minus 3 here. And from 6 to 2, we have also minus 3. But 2 is visited here. The edge is minus 3. What was going to happen here? We're going to check the distance between 1 and 2, and we will compare it with the distance between 1 and 2 passing by 3, 4, 5, 4, 6. So this is at 2 is 2. This is at 6 is minus 3. Minus 3 plus minus 3 is equal to minus 6. So they are different. So we can see here that this observation is broken because the distances between 1 and 2 taken 2 different paths are not the same. So we cannot make an arrangement using these conditions because one of these conditions violates the arrangement. In our case, 3, 5, minus 2. Share this picture. Okay. This first observation leads us to the second one. We have to check all paths from a starting point. If all paths return the same distance from the starting node to each node, so we return true. Otherwise, which means if there is one path given or gives us a different result, we return false. So in general, we can say we have a starting point, let's call it as 1. We have to check the path, all the paths, if they have all the same distance from S1 to that node A. So if these all paths have the same distance from S1 to a node A, so we return true. Then we check another node from S1 to another node, let's call it B for example. If all these paths have the same distance, so we return true. And so on until the end of the graph. Node n or n minus 1. Okay. If just one node gives me a different distance, let's say that's one path here, give me a different distance, so we return false in this case. From here we have to check from the same starting point. For example, here Well, this graph contains 14 nodes, but the graph is not connected. As you see, we have this subgraph and this one and this subgraph and this one. Okay, so we have to check from all the nodes. From the nodes is I goes from 1 to n, or 0 n minus 1, and check if that node A is not visited. If node A, node I is not visited, so we perform a DFS on that node I. For two reasons here. We choose a DFS. First, we can compute the array or the distances from the starting point to the other nodes using DFS. And we're going to mark each processed node as visit. So to not recompute it another time. Okay. Let's take this example here, for example. For this graph, here first we start from 1, and we perform a DFS. You see here DFS from 1 and so on, and we check that this is, for example, here this is from 1 to 2 here, and let's change the color. This is from 1 to 2 here. Is it the same with distance, for example, from 1 to 2? If they are the same, we continue to check another distance. For example, this one from 1 to 2. Okay. From 1, let's take another node from 1 to 3, for example, this distance. We go check if that distance is the same with this distance, for example, from 1 to 3. Okay, or this distance, another path from here to here to here, here, and okay. If they are the same distances, so all the nodes have the same distances, so we return true for this graph. Of course, all the nodes are visited, as you see, so we go to this node. We start in the starting node here, and this subgraph is 7. We check this graph, and we go to another starting point, which is 12 here. We check this graph, and we go the first 11 here, so one node will return true, and we check 12 for this graph. Okay, so then we perform an end, a logic end in C++ is like this, or between all these results, this one, and this one, because one of them it might return false. Okay. Before I show you how all this stuff will work, let's see how to build a graph. I'm going to use adjacency list to build this graph. We can declare it in C++ like this. This is how to declare. One way, of course, to declare an adjacency list. And from the input, from the conditions here, we can consider that this is the node A, this is the node B, and this is the weight of the edge between A and B. So we have the node A, the node B. So we can go from A to B with the edge with weight D, or from B to A with the edge from minus D, because in the problem statement they said if the soldier A is in front soldier B, so the distance will be positive, so we have D. Or if B is behind, of course, if A is in front B, so B is behind A, so it will be minus D negative. If you get this, you can back to the problem statement and see what I'm talking about here. Okay, let's take an example here. Before the example here, we have how to fill our adjacency list. So node A to B with D, and node B to A with minus D. Okay, let's take this example. So we're going to let's draw our adjacency list. We will start from 0. Okay. 0, 2, 2, here is 2, 2, 5. 3, 4, and 5. Because in C++, the arrays and vectors are 0-based indexed. And here in the public statement, all the edges or the nodes, are 1-based index. So we have to subtract one from each node here. So here we have 1, 2, 2, which means that we can go from 1 to 2 using the edge 2, which means is 1. Soldier 1 is in front soldier 2 by 2 units. This one. Okay, so we can say that soldier 2 is behind soldier 1 by minus 2 units. This one. Okay, how to represent this in the adjacency list? So 1 becomes 0, so node 0 here, this one, will be connected to the, we're going to address an array here inside the set. Will be connected to soldier or node 1, this one, this node here, 1, the edge is 2. Okay, and node 1 will be connected with node 0 with edge minus 2. So now the node will be changed. This is 0 and this is 1. As you see, node 0, this one, is connected to the node 1 edge with edge 2, and node 1, this one here, is connected to the node 0 here with the edge minus 2, this edge. Okay, let's read the second edge here, 2, 3, 4. So we can say that node 1 is connected to node 2 by the edge with its weight is 4. So node 1 is connected to the node 2 with 4. This is connected. This is node 2 with 4. Here's the color. Connect node 2 with 4. Node 1. And also the node 2. So we have an array here. The node 2 is connected to the node 1 by minus 4. Okay, this is how to build our adjacency list. I'm not going to fill all the example. It will be a little bit long. So you can do this by yourself to understand how to build the graph. After building the graph, we perform a DFS like we have seen previously to have this result. This is the code that came to my mind in the first time. Let's see how it works, how it will work in details. So we start. This is our starting point. We run a DFS on that point, DFS1. We marked as visited, and we check its neighbors. So we can go to 2 here, node 2. We check if node 2 is visited. It's not visited, node 2. So we go to the next condition. So the node 2 is not visited. So we update its distance. So the distance from 1 to 2 is 2 by using this formula. So here the distance of 2, which is 0, will be the distance of node, which is distance from 1 to 1 is 0, and we add the weight of the edge, which is D here, the weight of the edge. We suppose here you know this syntax in C++. So don't forget that, and we have an adjacency list of pairs here. So the first part of the pair is the node, and the second part is the weight of the node, as we have seen how when we built the graph. Okay, so the distance here will be the distance from the parent node, which is 1 here, plus the weight, which is 2 here. So the total distance will be 2. So from 1 to 2 we have 2. And we perform a DFS on 2, this recursive function. So we perform a DFS with 2. So we mark it as visited. See here in green. We check its neighbors. We have 2 neighbors of 2 here, 4 and 3. Let's say we go to 3. Check 3 is visited or not. In this case, it's not visited. And if is not visited, so we update its distance. So distance from 1 to 3 is the distance from 1 to 2 plus the weight from 2 to 3, which is 4 here. So we add that the distance. We have 6 here. 2 plus 4 is 6, and we DFS on 3. So we mark as visited. Check its neighbors. We have 5 and 2. Let's say that we go to 2 here. What will happen? 2 is visited. So, which means 2 is visited, which means that its distance is pre-computed, is calculated. Because it is visited, so we are sure that we have a distance here from 1 to 2, the previous distance. So we will check now if this new distance from 1 to going from passenger through 3, 1, 2, 3, 2 is the same or not. As we have seen in the previous observation 1, the distance from 1 to 2 must be the same with the distance from 1, 2, 3, 2. Okay? So node 2 is visited, so we'll check the distance here. The distance of 2 and 2 is 2. The neighbor is 2 here, or neighbor of 3, because we are in the DFS 3. The neighbor of 3 is 2. So the distance of 2, which is 2, we check is it different or not of the distance of that node 3 plus the edge minus 4. So the distance is on 3 is 6. 6 minus 4 is 2. So we have the same distance here, so this condition is not satisfied. So we continue. We do nothing here, we continue. Node 2 is visited, so we do nothing, we don't perform another DFS. Of course, it does not make sense if we perform another DFS on the same visited node 2. So we check for the other neighbors of the node 3 because we perform a DFS of 3. So the other neighbor is 5, as you see here in the graph, it will be red. We check 5 is visited or not. 5 is not visited, so this condition is not satisfied. But this one is satisfied. So 5 is not visited, so we compute its distance from 1 to 5. Okay, which is the distance from 1 to 3, which is 6. We add the weight minus 10. It will be minus 4. And we perform a DFS on 5. We mark 5 as visited. We check its neighbors. We can go to 4 here, the neighbor 4, from 5 to 4. 4 is not visited, so we update its distance, which is the distance from 1 to 5 plus the weight from 5 to 4, which is 4. So the old distance, it will be here 0. 4 minus 4 plus 4 is 0. And we perform a DFS on 4. We mark it as visited. We check the neighbors of 4. We can go to 2. From 4 to 2, we can go to 2. 2 here is visited. So we have checked the distance. Because 2 is visited, so we are sure that we have the distance from 1 to 2 is pre-computed. So we check if we have the same distance or not. Which means here, the distance from 1 to 2, we're going to check here. The distance from 1 to 2, is it different or not from the distance from 1 to 2 passing through 2, 3, 5, 4. If they are the same or not. Here, the distance are not the same because we can check together distance of 2, the neighbor 2, it's 2, and this is from node, which is 4, to node 4, which is minus 4, minus 4, 0, here, distance at 4 is 0, plus the weight from 4 to 2, 4 to 2 is minus 6, so this is minus 6. 2 is different of minus 6, okay? So we didn't find the same distance here from 1 to 2. There's another path we haven't have the different distance, so we return false. In that case, what will happen? So DFS4 will return false, as you see here, and we back. So and no need to continue with the node 4 because we terminate this call DFS4. This call of DFS4 is terminated by this return false. So no need to continue with the DFS4, and we backtrack to 5. Backtrack to 5, and we check the neighbors, the other neighbors of 5, not non-explored neighbors. We have 3, so now 3 is visited, and we check if the distance from 1 to 3 is equal is the same as the distance from 1 to 3 passing by 5, which means here distance from 1 to 3, which is 6. Is it the same from distance from 1 to here we have 2, okay, 2, 3, 5, 3. So this is from 1 to 3. Same here from 1. From 1 to 3 is 6. Let's compute this. Distance from this is at 3 is 6. Okay, the node, the parent of 3 is 5, so distance of 5 is minus 4. Minus 4 plus the weight 10, this weight here, 10 is equal to 6. So we have the same distance. So in this case, so here we have this, nothing happened because this condition is not satisfied. So we check the other neighbors of 5. There is no neighbors, so we return 2. Because we have the same distance, there is no other neighbors, so we find that the distances are the same. We turn to DFS 5, return 2. So we backtrack to 3 because 5 is all the neighbors of 5 are explored. So we backtrack to 3 and we check the other neighbors of 3. All the neighbors of 3 are explored. So at the end of this for loop, we return true. Okay. We backtrack to 2. We check the other neighbors of 2. Say that we go to 4. 4 is visited. So we check the distance. If you have the same distance from 1 to 4, pass by 2. So we have here distance of 4, 2, distance of 2 plus the edge 6. This at 4 is 0. This at 2, 2 plus 6 is equal to 8. So this is at 4 should be 8, not 0. Okay. But here we have 0. So this is not the same. So we return false. So the DFS of 2 return false. And no need to continue with 2. Because from 2 we have from 2 to 4 we have false. So we need to continue with 2 because 2 return we have found is just one path. One path. If we have one path return return false, so no need to see the other paths. So we backtrack to 1. Then this is the end here. 1 we have no neighbors, so no neighbors. 1 return true. So in this case, this is the end of all the codes. We return true. The DFS at the end, the first call return true. And this also will return true. Okay. And this is a mistake because, as you know, this case, the result must be no, because we have this edge here does not satisfy this arrangement, as we have seen in the beginning of the problem. So what's wrong with this code? This code is wrong. So we have to store the answer. If we come back here, we have found false here. So when we found false, so these two codes must return false. False. Because once we have false, as we see in recursion, the result will go up. This is the result. So we have to take this result. We have to, in another word, we have to propagate this result. And the stack of the codes, the result will be propagated to the top. So we have to propagate this result false to the first call here, and this is our answer. How to do this? We have to store the answer. So we can use another parameter and the function DFS to store the answer here. You see here, and the call of that function, the result of that function will be stored in that variable. We can use a parameter or a global variable. Okay. I think, I don't know if we can use a local variable. I don't know that. Just here, this is work for me. I know this, and the global variable, we can use a global variable to store the answers. Okay. So here we have to introduce or to use a global a variable flag. First, we will call it as true, and we call in the main program. The first value of that variable is true, and we will perform our DFS. Okay. DFS 1 is 1 and 2. We mark it as visited. Check the neighbors. So here flag is still true because so we do nothing. The condition is not satisfied. Same here, the condition is not satisfied because 2 is not visited. 2 is not visited. We update the distance. The distance from 1 to 2 is 2, and the variable flag will take the result of the DFS. 2 true. Okay. We perform the DFS 2 true. We mark 2 as visited. Check its neighbors. We have 3 here. We go to 3. The condition is not satisfied. 3 is not visited. So we update its distance, which is 6 here, and flag will take the result of DFS 3 true. Okay. Perform DFS on 3, marked as visited. Check its neighbor. We take the same path as the first previous example. Okay. We go to 3. Flag is still true, so nothing happened here. So now 2 is visited. See, and we check the distance from 1 to 2 is 2, and the distance from 1 to 2 passing through 3 so on is 2 also. So that this condition is not satisfied, so nothing happened here. 2 is visited, so we skip that condition. The other neighbors, we go the next neighbor of 3, which is 5. Nothing happened here because flag is set true. 5 is not visited, so we update its distance, which is -4, and the result of DFS 5 2 will be stored in the variable flag. With DFS 5, mark it as visited, check its neighbors. We go to 4, we skip that condition. 4 is not visited, so we update its distance, and we call DFS 4 true, and the variable flag will be stored. Its result will be stored in the variable flag. We perform a DFS on 4, check its neighbors. We can go to 2, flag is true, 2 is visited, and the distance now are not the same. Distance between 1 and 2, which is 2, and distance between 1 and 2, but we pass through 3, 5, and 4. They're not the same. So here we return false. So the DFS 4 true will return false. Now that false result will be restored in the variable flag. Here is how the recursion works. It's a good opportunity to understand how recursion works and how DFS works using the recursion function. So flag will be false. So that we call the variable, the parameter flag will be changed from true to false, and no need to continue with the edge with the node 4, and we backtrack to 5. Of course, flag is changed, so from true to false. So DFS 5 false. We check the other neighbors of 5. See now what will happen in this condition. Now there is no need to continue to process 3 to see is visited or not, or all of the stuff, So just when flag is false, just skip that node and backtrack to the previous code, to the previous node, until to reach the top of the stack here. Okay, so we return false because the flag is false now. So DFS of 5 is false. No need to continue with 5, and we backtrack to 3. We check the other neighbors of 3. There is no neighbors, so we return flag. We return false, which is false. So DFS of 3 will return flag because here there is no neighbors or 3 other neighbors, no non-explored neighbors. So this is the end of the loop for the node 3, and we go back after that loop. We have a return flag, which is false. So, and we backtrack to 2. Backtrack to 2. See the neighbors of 2. We can go to 4, but here there's no need to process 4 because flag is false. We have, which means we have found 2 paths that have a different distances. So we skip all the other stuff. So a not flag is return true. So we return false. So here, so which means DFS 2 false return false, and no need to continue with the edge 2, the node 2. After return of false here, we need to continue with 2. So we backtrack to DFS to call DFS1 will be DFS1 false now. So, and this is no neighbors for 1. We return a flag which is false, as we see, and this is the end of the code. So this is now our DFS. We return false for this input. Okay. Now let's check how to compute all the answers. As you see, the graph might be like this, non-connected graph. So we have to check. We have to and all the answers here with this value. We have true at the beginning because we know that true and false will give me false. So, for example, here, if this graph will give me true, and this one give me false, okay, and this one give me true. So the answer is false. True and false, and true will be false. Okay. This is the code is accepted. This code is accepted. So here we have our input. First, we have to initialize the array of visited for each node to false, and the array of distance to 0. And we build our graph as we have seen, and we perform a DFS on each starting point. Okay. And they have seen how DFS work. I hope this video is helpful for you guys. Thank you for watching.